get on. Our next speaker is Toma Scrivan, who I once incorrectly tweeted as Thomas Scrivnan, which seemed to amuse some people. But he's going to tell us about his work on automatic differentiation in Lean. Over to you, Tomasz.
Okay, thank you. Can you see my slides?
Yes, it's fine.
Okay, very good. Okay, so I'm going to talk about automatic differentiation in Lean. And first, what is automatic differentiation? Automatic differentiation is a process of synthesizing, generating derivatives of programs. So for example, if you have function foo, which takes x and produces x squared, then the automatic differentiation generates new function f prime, which takes x and produces x 2 times x, which is the derivative. And this tool has many applications, mainly in machine learning, especially when training neural networks, also in optimizations, and in general, like in scientific computing, when you solve, for example, differential equations. And all of these fields are extremely math heavy. And therefore, I think that Lean, because it's a theorem prover, might be a really good language for these fields. So therefore, I'm working on a library for scientific computing called Scilene. And automatic differentiation is part of it. And in this talk, I'm going to talk about how I did that. One kind of natural question is, there's so many frameworks and libraries for automatic differentiation. Do we really need a new one? Is Lean really special such that it can offer us something new for automatic differentiation? And I believe so. One of the problems in scientific computing is that we cannot compute the answers exactly. So we have to resort to approximation. And the problem with approximations is that they do not compose very well, and they do not work very well with differentiation. So for example, when we compute something and we talk about some function f, it can contain, I don't know, integrals and solving some nonlinear equation we cannot solve analytically on a paper. So when we write it on a paper, we have to resort to approximation. So the only thing that the computer sees is some kind of approximate function. And then the automatic differentiation can work only with this implementation, and therefore it cannot give you a really reasonable answer for differentiating this original function f. It just produces a constant zero. And this is a problem. But in Lean, what is really nice is that we can actually talk about this function because it can have some mathematical description. We can also talk about the process of turning this nice mathematical function into its approximation. And therefore, Lean hopefully can tell us, hey, you really don't want to differentiate this function. You would rather first differentiate it only then approximate it. Kind of related note is that standard automatic differentiation frameworks, they mostly ignore the question of differentiability. So for example, if we have a function sine, and we evaluate it a lot in zero, so we might want to short circuit it at zero with an if statement, and just if x is zero, then we quickly return zero without actually calculating the sine function. The problem is when we apply the standard automatic differentiation, the tool usually blindly differentiates each branch of the if statement. And you can see this gives you incorrect results because derivative of zero is zero. Therefore, it gives you incorrect derivative of sine at point zero. But in Lean, we can formulate the condition when this transformation is correct. We can ask, is derivative of zero and derivative of sine equal at a point x equals zero? And we can automatically try to prove this statement or prove the contrary and warn the users like, hey, here you probably want to change the implementation of this function when you want to automatically differentiate it. And there is a really nice overview article about lots of these problems with automatic differentiation. So if you're interested in these problems, I would recommend you looking at understanding automatic differentiation pitfalls. So in kind of general, my interest in using Lean for differentiation is that in Lean we can work with the ideal mathematical objects, and this, I think, we can really fluidly allows us to combine the simple computation and numerical computation. To give you an example, when we want to solve differential equations, we can define a function which is called ODE solve, which as an input is a definition of differential equation. And what it does is just it asks if there exists a solution. If there exists, it returns the solution. Otherwise, it just gives up and returns zero. Such function is not really computable in any sense. you cannot really run this function. Therefore, it's written non-computable. So it's just a symbolic representation of it. But in many other languages, if you work with a symbolic kind of symbolic functions, usually there is a clear distinction which functions are the symbolic and which are like the normal function of the programming language. And like really symbolic / non-computable functions and normal functions are really indistinguishable from the perspective of the type system. So I believe it would really allow you to literally mix symbolic and numerical techniques when doing scientific computing. So, for example, you can state a theorem that if you take a solution of a differential equation and you differentiate it with respect to time, you just get the function f. Therefore, if you write a program using this function and you want to differentiate it, you just use this theorem to rewrite it. And then once you're ready to run the program, which you can use a different theorem, which just says, oh, the function OD solve can be approximated by some simple type stepping scheme. And because, yeah, we cannot compute the answers exactly, so we have to pick some approximation. So you just pick sufficiently high and to obtain a desired accuracy. To give it a little bit bigger picture, why I'm interested in using Lean for scientific computing is that in scientific computing, we want to model the world. And let's look at the process, how we do that. So if you want to model the world around us, we have to look around, formulate some mathematical model about the world. And then we have to reformulate it and usually kind of manipulate the equations such that it's in the form that we can actually write on the, we can implement on the computer. And this is usually done by hand. Then you have to go through the painstaking exercise of actually implementing it in some programming language. Then we can finally, run it. And don't know. There was animation of simulation. Unfortunately, it doesn't work. So what I would like to with Lean, I would like to directly write the model. I would like to write the model directly instead of Lean, and then hopefully let the computer do all the other steps automatically. And the hope is that in Lean is the right language for it, because because Lean is so expressive and extensible, all these steps should be expressible in Lean. Hoping that this would be all done automatically is too bold. It's too big of an ambition. So my hope is kind of that all these steps will be done automatically with the computer would do the parts which can be easily automated, like automatic differentiation, and the other parts which cannot be easily automated, like picking the right approximation, would be done by a human. And I think that Lean's interactivity would be great for this. So back to automatic differentiation, and let me tell you how I implemented in Lean. So I look at it a little bit more generally, and I implemented a tactic for general function transformation. I call it FTrends, and it's a tactic designed to prove statements like this: that the transformation of a composition is a composition of transformation. And example of such a transformation is differentiation, or taking a joint of linear function. Another example of such a transformation is forwards or reverse automatic differentiation, or vectorization, where you have a program operating on scalars and you want to turn it into a program operating on arrays, or isomorphism, when you have a program operating on some data structure and you have isomorphic data structure and you just want to translate the program to that other data structure. So example how you can use FTrends is, for example, here to compute the derivative of x squared. It's equal to, this is just equal to a linear function in dx, 2 times dx times x. You can prove it by FTrends. Or if you want to compute a joint of a function where you multiply by a complex unit, then this is equal a multiplication by a negative complex unit. Again, we can solve it by FTrends. So a bit how the tactic FTrends works, or how to set it up if you have a new function transformation. So it more or less works like a simplifier, but there is a few steps in extra to set it up. So first, you have to define a basic kind of lambda calculus rules. So you need to specify how identity function gets transformed, how composition. Here's example how the relevant terms for derivatives. Then what you have to do, you have to register this new function transformation together with these lambda calculus rules. And then you can mark relevant theorems the same ways as with the simplifier, just adding attribute FTrends to relevant theorems. And for example, the derivative of addition should be formulated such that you introduce to auxiliary function f and g, and then the derivative of f plus g is just derivative of f plus derivative of g. And if you want to have a look how this is all set up, just look at this file in the Silent library. So in the tandem of the FTrends tactic, there is also the tactic FProp, which is used for proving function properties like differentiability, linearity, continuity. Again, like it is designed for proving that the property of composition is true if the property of Fn, Fng are true. You might think that there is already a tactic for stuff like this in MATLAB, which is called continuity, which is backed up by ASOP. But why I'm actually implementing FProp is that it's tightly integrated with the FTrends tactic. Because when you do some function transformation, you often have to prove that certain subfunctions are differentiable and over. So what FTrends does is caches during the transformation the results of FProp. Therefore, it can be much faster. Also, continuity is not really designed to deal with the expressions that look like programs. So, for example, this expression it's not really common to encounter expression like this when writing mathematics, but it's very common when you write programs. So proving that such a function is continuous with continuity, it takes roughly 1 second, but then when you use FProp, it takes just a couple of milliseconds. Another difference from continuity tactic is that it is much better in handling functions with multiple arguments. So if you have a binary operation which is jointly continuous in both arguments, then proving that f of x and x is continuous in x, it can be solved with FProp. I had a hard time proving with continuity. Or when you're dealing with a higher order functions, so when you want to prove that the composition of f and g is continuous, and f actually returns a function, then there is a problem, I think, with some higher function, with the unification of higher order functions, and continuity doesn't work. So let me show you a few examples in VS Code. So here is the example as you could see in the presentation. So it's just that the function x squared is continuous or differentiable, solved by FProp. You can also, for example, show that x plus 2 times x is a linear function. Right. And then to transform a function, when we compute a derivative of x squared, I hope my internet didn't die.
Oh. We still see you. I think you're
good.
fine.
Okay, yeah, I just got freaked out because I have some issues with internet. Okay, good. Okay, so when we want to compute a derivative of x squared, right? It's a linear function in dx, and it's equal to 2 times dx times x. You can solve it by FTrends, but what is important that this is a conf tactic, so you can write that you can zoom in on the left hand side, and then by calling FTrends, it just transforms the x squared into 2 times x dx to x. So what is nice about this is that you can actually run this tactic during elaboration. So I have kind of, I think, nice notation for computed derivatives. So let's again compute a derivative of x squared, and to do that you just write partial x, and this says please compute the derivative with respect to x of type r of the expression r squared. Right? And to actually compute the derivative, you just add an exclamation mark, and you can see that it is just 2 times x, or here this is function in t times 2 times t. So what is important, because I'm interested in differentiating programs, so when you have expression like this and you compute the derivative, it should not destroy the structure of this expression. So I just add an exclamation mark to run differentiation. And after some pondering and looking at this, you can will be able to see that the original computation is kind of interleaved with the computation of the derivative. In many applications, like in physics and optimization, you quite often don't want to compute a simple derivative, but you want to compute a gradient, which just takes a function from some inner product space that goes to real numbers and produces a kind of direction at every point where the function increases. So let's look at a function that is defined over r squared. And it just takes x and produces a projection to the first component. Okay, and we want to compute the gradient of this. This should be just a constant vector field 1, 0. We added an exclamation mark, and it's exactly as one would expect. Oh, yeah, it's a constant vector field 1, 0. Another common function that one might want to compute the gradient of is a norm. So if we take a 2 norm squared of x, then the gradient of this is just 2 times x. Oops, yeah, 2 times x. When it comes to differentiating programs, there are two main different ways how you want to differentiate it. And one is called the forward mode, and the other the reverse mode, automatic differentiation. What the forward mode automatic differentiation is doing is that it takes a function and produces a function that takes the input x and the change of the input and produces a pair, which is the value of the original program and the derivative of the program with respect to x. So for example, and the notation is again derivative, and I just added like this little arrow to indicate like arrow forward to do forward differentiation. And if we check what's the answer, it is the value of the program, and this is the derivative as we expect. In the reverse mode, the derivative goes the opposite direction. So the reverse mode differentiation, it takes a function and produces a function that produces a pair. Again, it produces the value of the program itself. But the derivative, it actually takes a change of the output and produces what should be the change of the input. So when we compute the reverse derivative of the projection to the first component, we get the original function. And then here we get, if we change the output by dy, then we should change the output by dy, by a pair dy 0. So these are kind of the four basic operators to do differentiation, and you can use it with the tactic FTrends to compute whatever derivative you want, and it works really nicely with the basic arithmetic operations. But when you write program, you quite often write your own functions, and you need to make sure that the system works with your own defined functions. So when you define a function here, foo of x and y, if you would try to differentiate it right now, then it would not do anything. What is necessary, you need to write down all the kind of the necessary theorems that this function is differentiable and that the derivative of foo is something. So rather than writing it yourself, there is a command generate a forward derivative of the function foo with respect to x and y, and it gives you two goals. It asks you to first show that this function is differentiable, and it asks you to compute the derivative. And this can be done just simply unfolding the definition of foo and calling fprop or FTrends. And you can then check it automatically generates theorems like this. There's some naming convention. It says that the function foo in argument x and y is differentiable. And you can see that it kind of says if x is differentiable and y is differentiable, then the foo of x and y is differentiable. It defines a new function that computes the forward derivative, and here is a theorem that formalizes that if you compute the derivative of foo, then you should use this newly defined function. And if we actually compute the function, if you derivative of the foo, then you can see it uses the newly defined function. So this is fairly boring example of differentiation. It can be used in much more complicated example. So let me show you. So the prime example of automated differentiation is machine learning. So I would like to implement a simple neural network purely in Lean. So unfortunately, it's not working yet. I was unable to train it. But here is a definition of simple neural network that this is just a function that accepts weights and biases on the first argument, and the second argument is an image which is 28 by 28 pixels. And then you just set up a simple neural network like convolution, nonlinearity, pooling, dense layer, again nonlinearity, another dense layer, and then you just clamp it the values between 0 and 1. With this command, I just generate first. Here, I prove that this function is actually differentiable in the argument W. And here I just compute the derivative of the neural network using FTrends. And what is nice, I'll try to convince you that it's actually doing backpropagation, which is kind of the main algorithm to compute derivatives. So if you look at, the backpropagation is consisting on the forward mode. This is the forward mode, and this is the backward mode. And the forward mode, the forward pass. The forward pass is nothing else but the original program. So, for example, you can see that the convolution here is again the first step of the new programs. But the convolution, the original convolution, is replaced by a function that also computes the reverse derivative. So this value is the result of the first layer, but also it gives you a function how to compute the derivative in the forward pass. And if you look at the forward pass, this value is used exactly at the end. So it really it runs the original program in the reverse, slightly modified. Another nice thing, I think, doing this in Lean, for example, you can just look at the definition of one of the layers. So I can look at what's the definition of convolution. And this really resembles the mathematical definition you can see in a textbook. So convolution, the inputs are some weights, some bias, and the input image. And the result is some array with some indices. You say bias plus, and here it's really like the convolution where you sum over the indices of the weights. And here you kind of index into the image, but you shift it by the index of the weights itself. And here, I just generate the derivatives, and I think it's nice that you can again inspect the derivative of the convolution layer. And if you spend some time just looking at it and trying to decipher it, then you realize that it's doing something relatively reasonable. So yeah, so with that, I would like to conclude. And just say that, yeah, I'm working on a library for scientific computing in Lean, because Lean is a nice programming language, but also a theorem prover, and scientific computing is very mathematical. So I think that would be a good match. And I implemented a forward and reverse mode automatic differentiation using a fairly general function transformation framework, which is based on two tactics, FTrends and FProp, for relatively general function transformation, and FProp for proving properties. So there's lots of work I want to do in the future. So first, I think now it's in a fairly stable shape. So I really want to document it and improve the user experience, such that there are lots of kind of awkward things which should be improved. Also, the error reporting should be much better. But I also would like to integrate a little bit with Mathlib. I had a little bit issue with using the Fresher derivative in Mathlib, because it depends on the norm, and this was causing me some issues, in particular that the product space has two different norms. I would like to use the L2 norm, but by default is using Aleph with a norm, and that was causing me some issues. So I think when it's integrated a little bit with Mathlib, then I would like to really prove all the transformation rules, and then I think I would have an automatic differentiation which is proven to be correct down to epsilon and deltas. And there's many other directions I would like to explore afterwards. I should handle better mutable variables. There's also a big question. Right now, I differentiate only functions between vector spaces. I would like to do between manifolds. I'd like to differentiate much better with respect to functions, so do stuff like variational calculus and any other stuff. So I think that's all from me. So I would like to thank for your attention, and anyone has any questions.
Thank you very much indeed for that rather extraordinary talk. I think the first person with their hand up was Yanis. Go for it.
Yes. Thank you. Great, great talk. I have two questions. One, can you define? Can you differentiate functions? For example, one example I had in my mind is the exponential of -1/x², which is not differentiable at 0 unless you define the f of 0 to be 0. And I was wondering if with a function that you define like that, will your program understand if it's differentiable or not?
So right now I'm mostly focusing on, because most of the application of automatic differentiation, the functions are kind of obviously differentiable. So right now I'm focusing on that.
Okay.
At some point I would like to focus exactly, I don't know, yeah, handling division, such that then you have to kind of prove sub goals that the arguments are away from zeros, and then I think I have some tools set up for that, but it's not my main focus right now.
I see.
So,
okay. And also, can you parametrically change the norm? For example, can you work with norms in LP, for example, or you do only L2?
No, the kind of the real. I think there is no problem to work with different norms. There is only a problem that kind of what is the natural type class, like what the type class systems derives, what kind of norm it derives by default on a type, and that's kind of my issue. And by default, it uses infinity norm. And because I want to do compute gradients where you really need inner product spaces, yeah, then this is kind of a trouble. So, but yeah, like computing with different norms, it's okay.
Yes, the fact that Mathlib has chosen the L infinity norm has caused other people problems in the past as well. I think Yuri was next. Go for it, Yuri.
So, thank you for the talk. My question is also related to functions that are not everywhere differentiable. More precisely, I have maybe several questions. One is, did you consider using has, f, deriv, at, and things like that to avoid proving differentiability over and over again, or even if you reuse some proofs? And second is, if you want to deal with higher order derivatives, and you have a function that is not everywhere differentiable, then you need to do some trick. You need to prove that the first derivative is given by something in a neighborhood of a point, and then second derivative is given by the formula in the neighborhood of a point to be able to proceed further. Did you think in this direction or not yet? What are your...
So yeah, I have a little bit experimentation with instead of proving differentiable on the whole domain, I have some experimentation where you differentiate it when you prove differentiable only at a particular point. But I haven't really combined it with any powerful tactic that would actually show, for example, that the point where you differentiate is really away from zero and stuff like that. So yeah, I haven't done that many experimentation in that direction.
Thank you. Just my reason for asking the question was I once tried to formalize Schwarzen derivative, and it was a mess because you need to do some things with higher order derivatives, and it's not convenient at all. Thank you.
Yeah, but yeah, there's one thing I was also like to look into is like proving differentiability on automatically on